end of the presentation, you should be able to answer all these questions. Alright, STP. STP is standard temperature and pressure, and we're talking about thermochemistry. It's going to be 25 degrees Celsius or 298 Kelvin. We're not going to worry about pressure so much as standard temperature. So all reactions either release or absorb energy, and we abbreviate energy with a capital E. Heat energy is referred to as enthalpy, or change in H. Your units are going to be joules or kilojoules, and we can really only measure changes in enthalpy. And this is Hess's law equation, which we'll get to in a bit. Alright, so here are all the different forms of energy that y'all should know. We've talked about electromagnetic energy and nuclear energy. Electrical and mechanical energy are really more physics. We're going to be focusing on thermal energy, like melting ice cream or heating soup for this unit. Alright, exothermic reaction. An exothermic reaction, you release heat or energy. So if you look over here at the enthalpy graph, which y'all will have to know, the energy of the reactants is higher than the energy of the products. So you need energy to form bonds. So an exothermic reaction, you're forming chemical bonds. Down here you have an endothermic reaction where you absorb heat or energy. And here your energy of reactants is much lower than the energy of your product, so you have to overcome this activation barrier here to break bonds. So you're breaking chemical bonds. Alright, so this ice melting, that is an endothermic reaction. So if you hold an ice cube in your hand, it melts, right? Because it's absorbing energy from you, and it's breaking the strong intermolecular forces of a solid. And it's exactly the opposite for water. With water freezing is an exothermic process, because you have more energy in a liquid than you do in a solid. So you're releasing that energy. Okay, here is a temperature versus energy graph that y'all will have to know. On the diagonal lines is where you have your states of matter, and the flat lines is where all your phase changes occur. And there's no temperature change with phase changes. So temperature's on the y-axis and heat is on the x-axis. So as you go this way, you're going to warm, and here, right here, is going to be your melting point or your freezing point, depending on which way you're going. So here's your phase change. Your melting, freezing occurs on the flat line. Then you're a liquid, and right here at this point, that's your boiling point or your evaporation point. Then here you're condensing, you're boiling, your phase change is happening, and then your gas. Alright, specific heat. This is calorimetry. Q is energy. M is mass. C is your specific heat, which is unique to all substances. So you're going to have to either be given or look up specific heat. And T is temperature. And this little triangle means change. So we're looking for the change in temperature. So here's an example problem. How much heat is required to warm 400 grams of water from 20 degrees Celsius to 50 degrees Celsius? Well, I'm going to plug it to my equation here. So I'm looking for how much heat. So I'm looking for Q, and Q is mass, so my 400 grams, times my specific heat of water, which is 4.184. And I just know that off the top of my head, you would be given that, times the change in energy. And it's always your final temperature minus your initial temperature. So it's always what you end with minus with what you start with. So 50 minus 20 degrees. Okay, so we get 400 times 4.184 times 30, and you get 5,000, not 5,000, 50,000 joules. So this is how much heat was required. And if I want this in kilojoules, I'll have to divide by 1,000, and I could get it into kilojoules. Sometimes they'll ask me for kilojoules, so 50.208 kilojoules. Now if you look, this is a positive number. So if it's positive, that means it's an endothermic reaction. It absorbed heat, right? We're warming water, it's absorbing heat. If it was negative, it would have been an exothermic reaction. So you can tell by what type of reaction it is by the sign of your numbers what you get out of here. All right, Hess's law. If you add two or more thermochemical equations to give a final equation, then you can also add the heats of reaction to give the final heat of reaction. So what it's saying is I have this equation right here. This is what I want. I want to know how much heat was released. Well, I know the steps of formation. These are my steps, which you'll be given. So I have to manipulate these equations so that I can have the heat of formation. So I want this over here. So I know I need 2N2 over here. Well, I have an equation with N2 right here, but I want two of them. So I'm going to multiply this whole equation by N2 by 2 plus H2. And I'm not writing the states of matter, the solid, liquid, gas, but you really should. Now, if I multiply this by 2, then that means I have to multiply my heat of formation, my delta H, by 2. So my delta H for this reaction was negative 48.2. So I need to multiply that by 2. Okay. Now, I need two N2O5s on this side over here. Well, it's over here. So what I need to do is I need to flip it. And I also have two of them, so I need to multiply it by 2 and flip it. So I'm going to flip my equation around. I'm just going to write it backwards. So 2HNO3 will give me H2O plus N2O5. Okay, so my delta H, I need to multiply it by 2 because that's what I did to my equation, but I also need to change the sign since I flipped my equation around. So this would be plus 73.7, and then we'll multiply it by 2. Okay, so my last step, let's see, I've got 2H2O. Well, I don't need any H's, so I need to look back here. I've got H on the left side of the arrow here. So I want to cancel this out, so I'm going to need to flip this around too. And I have two H's, and when I multiply this by 2, I'll have two H's, so that I don't need to multiply it by anything. I just need to flip it. So 2H2O will give me O2 plus 2H2. Okay, and then I just need to change the sign of my reaction. Oops, 1.6. Okay, so then I'm going to go ahead and do all the math. So I multiplied all these by 2. So 2N2 plus 3O2. Oh, no. That should be a 6. 6O2 plus 2H2 gives me 4HNO3, and then 4HNO3. I'm going to go ahead and put all my arrows next to each other so I know what I can cancel. N2, oops, I'm multiplying 2, I forgot. O5. Alright, and then I've got 2H2O plus O2 gives me, no, that's not right either. Geez, I can't copy these things right. Okay, so H2O, okay, yields O2 plus H2. Okay. These I'm going to add up later. Okay, so now what I want to do is I want to go cancel things. So if it's on the, I can cancel what's on opposite sides of my arrow. So like this 4HNO3 can cancel. And that's fine, because if I look back up here, it's not in my equation that I want, so I don't need it anyway. My 2H2s can cancel, which I forgot to put a 2 down here. There's a 2 there from right here. And then my, what else can cancel? Oh, my waters can cancel. And I can cancel this O2, and that reduces this by 1. So I canceled out 1 O2. So if I rewrite this equation now, I hope y'all, this isn't going off screen. 2N2 plus 5O2 gives me 2N2O5, which is exactly what I have up here, so that works out perfectly. So now I just add all this up, which I didn't do beforehand, which I should have. So negative 348.2 times 2 plus 73.7 times 2 plus 571.6. Okay, so my change in, my change in H is 28.6 kilojoules for this equation. All right, so that was the long way. Here's a shorter way. So you have your delta H equals your, I forgot my triangles. Change in products minus your change in reactants. Okay, so you will need a table for this. You'll have to look up your delta H's of formation. If you have an something that's in its elemental state, like you have iron all by itself, or you have a diatomic like O2, N2, all those heats of formation are 0. Okay, so I want to find the heat of formation of this. So delta H is going to be the sum of my products minus the sum of my reactants. So my products, I've got 1 CO2. So I'm going to go down here as gas. So CO2 gas is negative 394 plus I've got 2 waters. And notice that this is in gas, so when I come down here I have to make sure I use my delta H for my gas. 242. Okay, so that's my products minus, I have 1 methane, my methane, negative 75 plus, this is diatomic now, so it's in its elemental state, so it's 0. And when you do the math, you should get negative 953 kilojoules per mole. Okay, now look, my sign is negative, right? This means this is an exothermic reaction, and that makes sense because this is combustion, you're releasing heat. Okay, all right, if you can't answer the questions at the beginning of the video, then please go watch the practice video.